So as we have seen in the construction of BCH and Goppa codes, the subfield subcodes are important in their construction. And as I mentioned in the previous video, indeed, we will be able to describe them in terms of, for the general setting, for the subfield subcodes, we will be able to describe them in terms of other notions like trace codes. And for this purpose, for given linear code fq to the m, because like in the BCH and Goppa, we consider an algebraic geometric code, which is defined over an extension field fq to the m. And these codes, BCH and Goppa codes, indeed are linear codes over fq, because we define the subfield subcodes as the linear code C intersection fq to the n. And we also define what is called trace code, which is obtained by applying the trace function of the each coordinates of a code word from given C. And here trace is defined as the sum of the conjugates of the given element from fq to the m. Indeed, this sum belongs to fq. You can check it by taking its q power and verify that indeed, again, it's equal to this sum. So trace alpha in fq because we can easily verify that trace alpha to the q is equal to trace alpha, and this map is fq linear. And just in case if you didn't come across this function before, or if you didn't take the course finite fields, let me also mention that trace is onto. And in order to see that this fq linear map, spatial fq linear map is onto, in order to see that it's enough to see that the existence of alpha in fq to the m, which has non-zero image. And then we can produce the all elements. We can find the pre-image of these elements C from fq. And in order to see that, first, let me note that if trace of alpha is 0 for an alpha from fq to the m, by the definition of the trace, alpha is going to be root of the polynomial of degree q to the m minus 1. And this is a polynomial with coefficients from fq, and because of its degree, it can have at most a root of the polynomial, and this polynomial can have at most q to the m minus 1 from fq to the m. But fq to the m has q to the m elements, so that means there exists at least one element which does not have its trace as 0. Okay, so now our claim is that our main purpose will be to see the relation of a subfield subcode, which is defined from a linear code fq to the m linear code of length n. More precisely, the dual of the subfield subcode, indeed the trace of C dual. Here the first inner product is determined by a bilinear form over fq, and indeed here we only consider the Euclidean inner product. And the second inner product, which appears here, denotes a bilinear form over fq to the m. And more precisely, in this theorem, we consider the Euclidean inner product over fq to the m. And in this equality is called Delsarte theorem. So first, let me just consider again BCH and Goppa. In both cases, for an algebraic geometric code, we were able to describe them, the dual of subfield subcode of the dual of an AG code. So in this equality, if we replace C by C dual, and if we take the dual of the both hand side, indeed we can write BCH and Goppa, or in general such structures, in terms of the trace code. So this theorem will be useful in the sense in our setting for this purpose. And now let me explain how we can see that indeed these codes are the same. And for this purpose, first, let me consider a vector from the left-hand side, and to show that indeed it also belongs to the dual of the restriction Q of the dual of the subfield subcode of C. And indeed our claim will be equivalently to see that for any C from the subfield subcode, it's going to be complement the trace of A for A from C dual. And if we write this code verse C and A explicitly by the coordinates, this inner product gives us the equality of the product of the component wise. Here by the trace A, what we want to mean is that the trace of each component of the code word A from CDU. And since trace is FQ linear and this CI's from with his coefficients from FQ, we can write this sum is a trace of the product of CI and AI. And indeed, let me also replace the sum and the trace because of the linearity of trace. And now let me note that this sum of the coordinates of AIs and CIs are indeed the inner product of the vectors A and C. Since we consider C from this intersection, so that means C is also belongs to C, and A is from C dual, this inner product is going to be 0, and the trace 0 is 0. And this shows us the first inequality. And in order to see the other inclusion, so that means the dual of the subfield subcodes of a linear code C lies in trace of the dual of C. We equivalently prove that for the vector spaces, as we have seen one of the discussion session, if we have two vector space A and B in FQ to them or in a finite dimensional vector space, with respect to this orthogonal complement or the dual definition, we can observe that the dual of B lies in the dual of A. So that means equivalently, it will be enough to show that the dual of the trace of dual C lies in subfield subcode of C. And to prove this towards a contradiction, we suppose not. So that means, let me suppose that there's a vector in this vector space, but not in C. Then for the vectors from C dual, we get the inner product U and V as non-zero. So since the trace map is not a zero map, so because it is on to and there exists the elements in the extension field FQ to the M such that the image of delta times this inner product, which is considered as a bilinear form over the extension field, has image under trace as non-zero. But on the other hand, by the properties of the bilinearity of the inner product, this inner product is going to be 0 because we consider U from the dual of trace of C dual, and since V is from C dual, gamma V from C dual, and this gives us contradiction.